Hello students, welcome to today's session on force vibration with damping, an important topic in the vibration analysis. An aerospace engineer. In this video, we will understand how system behavior when subjected to external forces and how damping plays a crucial role in the rolling controlling vibration. Let's begin. So, the learning objective of this course is defining the force vibration, distinction between free vibration and force vibration due to the external excitation forces. And also, we are going to see how the damping effect plays a vital role in the dynamic system. And also, we are going to model the system to examine the equation of motion like mx double dot plus cx dot plus kx equal to for applied force, and also we are going to do the analysis due to the resonance and with the practical application. Now, coming to the basic of vibration, before we begin, let's quickly recall free vibration. In free vibration, the system oscillates without any external forces and only initial condition drives the motion. The natural frequency is given by omega n is equal to root of k by m. Here, k is the stiffness and m is the mass of the system in the engineering system. Especially in the aircraft, external forces are always present, and that leads to the force vibration. So, what is the force vibration? It is the vibration of a system under an external periodic force. Unlike free vibration, here the system responds at the same natural frequency and the applied forces. The governing equation of the motion mx double dot plus cx dot plus kx equal to f sine omega t, where omega equal to natural frequency and m is equal to mass, c is the damping value. And also this equation foundation gives the vibrational analysis due to the first vibration. Next, now let's understand the damping in a critical concept. The damping presents energy dissipation in the system. There are three main types. One is viscous damping. This is due to the fluid resistance. Coulomb damping. This is due to the dry friction. And structural damping, which is that depends on metal behavior. The damping ratio is given by damping ratio zeta is equal to C by 2 root of Km, where C is the damping coefficient and K is stiffness and M is the mass. Based on the damping ratio, system definitely differently under damp oscillation gradually decays due to the critically damp. The critical damp, the faster return to the equilibrium. In over damp, the slower return to the oscillation. This classify the very important of the vibration system design. Coming to the mathematic modeling, to analyze the system response, we define key parameters in the natural frequency, damping ratio, and the frequency ratio. That is, omega is equal to omega n is equal to root of k by m, f is equal to damping ratio r equal to omega by omega n, damping ratio zeta is equal to c equal to root of 2 k by m. This is the steady state response. Consists of two parts. Transient response depends on initial condition and dies in a steady state. Steady state response continues as long as the force is applied. Engineering engineers mainly focus on steady state behavior for the design. Now coming to the most critical concept called resonance. Resonance occurs when the force frequency is approximately equal to the natural frequency, whereas omega equal to omega n gives the condition where the natural frequency system frequency matches. At this condition, the amplitude becomes maximum, which can be dangerous. The amplification factor 1 by 2 zeta root of 1 minus damping ratio zeta. So also the phase angle changes with the frequency. Lower frequency is 0 degree, and the resonance will happen at 90 degree, whereas higher frequency will produce and the 180 degree. So understanding this helps in vibration to control in the automotive suspensions, building isolations, and aerospace structures. Let's connect with this real world engineering application. In automotive suspension, the damping reduces the road shock waves and the buildings helps to resist earthquake. In aerospace, it's extremely critical, especially in the controlling flutter in the tail section, also in the main wing section, which can lead to structural failure in the aircraft. So vibration controls is not just theory; it is a safety requirement in a operation. Coming to the summarization, the force vibration occurs due to excitation. Damping controls the amplitudes, and system stability resonance is the critical condition to avoid engineers used in the mathematical modeling, so that the design can be more safer and more in the high efficiently operation. So this topic is very important for examination like GATE and also for the real aerospace application. So the finally this course help us to have what's the force vibration and this equation, what are the damping effects on the system response, and also the several practical applications in applied in the aerospace engineer. Thanks for watching. In the next video, we'll explore more on advanced vibration concept. Thank